So we start today's lecture by looking at another kind of fundamental aspect of the field equations before we move on and talk about the applications, which is what we're going to do pretty much in the next lectures. In fact, for the rest of the course, we are going to look at how you solve the field equations in different contexts and what kind of solutions you get. But before we get into that, one aspect which I think is very interesting is how you get the field equations from a variational principle. So you're familiar already in classical mechanics that you do the variation of the action and you set that equal to 0, right? And from that you get usually Lagrange's equation, right? So it's a well-known fact that you can derive, in fact, most of the differential equations of classical physics from some sort of variational principle. And the same applies to gravity. Now, what is interesting about gravity is that the variational principle is very simple, right? So what you look at is IE is equal to minus 1 over 16 pi g times the integral in d4x times square root of g. So you look at the integral over a volume element, right? Remember that the volume element, which is general coordinate invariant, is not d4x, but is d4x times the square root of the determinant of the metric, right? And, well, the action has to be a scalar, right? Because the action is a quantity that's not supposed to have any indices attached to it. And so the question is, what can you put in here that is a scalar? Because this quantity is a scalar, and you multiply by another scalar, you get a scalar, and that would be fine. And, well, there's not that many scalars you can construct out of the curvature, right? If you just restrict yourself to first and second derivatives. So that means that the only candidate that you have here is the scalar curvature, right? And this was proposed by Hilbert in 1915, right? And so as a result, this is called the Einstein-Hilbert action. Einstein-Hilbert action. And of course, at this point, we're just looking at the gravitational field only, because in general, of course, we will have also the matter part, right, about which we'll talk a little bit later. And so I think at this stage, it would perhaps be interesting to see how you get that out of this action. When you vary it, you get the classical field equation. So we are interested in doing the variation of this Einstein action and set that equal to 0, right? And so that means that we have to vary what appears inside the integrand. And so we have to do the variation of the square root of g times r, right? Now remember, the Ricci scalar is a contraction of the Ricci tensor. So we can write this as, because this r is equal to g mu nu times r mu nu, right? We can stick that in there, and when you do the variation, we get 3 terms, right? So we get the square root of g times r mu nu times dg mu nu. Okay. Then we get r times the variation of the volume element, right? d root g. And then the last term is root g times g mu nu times dg mu nu, times the variation of r mu nu, I mean. And so we have to evaluate these variations individually, right? And, well, it turns out that the first term does not really much to do to it because it's already in the correct form. We would like to write the whole variation as something that multiplies dg mu nu. And it doesn't really matter that much whether the indices are upstairs or downstairs. And so this term has already the dg mu nu explicitly. And so we don't need to do any work on that. This one, the variation of the volume element, has to be written in terms of variation of the g mu nu, which is fairly easy to do. And the real messy term is the third one, right? The variation of r mu nu. Because we have to look up what the definition is of the Ricci tensor and see what we get. So let's look at the variation of the Ricci tensor. So let's do the variation of R mu k. And well, we have to go back to the definition, right? Remember the definition of Riemann itself was that Riemann was equal to some derivative of gamma minus some other derivative of gamma plus gamma gamma minus gamma gamma, right? So when we do the variation, this is for Riemann itself, but Ricci is just a contraction of that. So the first term we're going to get is some variation of the gamma, right? And then at some later stage, we also have to use the fact that the gamma is 1/2 times g to the minus 1 times dg plus dg minus dg, right? So that's going to come in at second stage. So we get first the derivative of the variation, taking a derivative and doing a variation commute, so we can do it in any order we wish. And so this is the variation of gamma lambda mu lambda divided by dxk plus dot dot dot, right? So there's a number of other terms. And in this expression here, we have to stick the variation in gamma that we get from varying this whole expression, right? So the variation of gamma lambda mu nu is from the formulas that I gave in the previous lectures, minus g lambda rho times g rho sigma times the variation of this times gamma sigma mu nu plus dot dot dot. So there's lots of terms, and this is a really complicated thing. But there is an identity. So there is a magic identity. There is a magic identity that says that if you do look at the variations of the Riemann tensor, the Ricci tensor in this case, the variation of R mu nu can be written as a combination of covariant derivatives. And so we write delta R mu k is equal to the variation of gamma lambda mu k, and then semicolon, that is covariant derivative with respect to lambda. Actually, sorry, it's the other way around. This should be a lambda, and that should be a k. Okay, like this. And then minus another derivative of variation, which is the variation of gamma lambda mu k, gamma lambda mu k, and then semicolon lambda, like this. And this is called the Palatini identity. It's called the Palatini identity. And if you write out what this Palatini identity implies, it basically tells us that the variation of R mu nu is a total derivative. And so what you get from this by a few additional manipulations is that when you multiply this by g mu nu, so in other words, if you do g mu nu times dr mu nu, which is what we have here, right? This, in fact, because of the Palatini identity, this is minus delta g mu nu plus g mu nu g alpha beta times dg alpha beta, and then semicolon mu and semicolon nu. So in other words, the combination that appears in the variation can be written as some combination of the metric, which is pretty simple, right? We've gone down from the initial complexity of having the Ricci tensor to having the affine connection. But in the end, you just get the metric, and what you have to do is then calculate two covariant derivatives. So there's semicolon mu and semicolon nu. Well, what this actually tells us very simply is that this thing is a derivative. Clearly, it's a total derivative. The variation of g mu nu with respect to the variation of R mu nu times the g mu nu is a total derivative. It's a total derivative, which means that whenever you have the integral of a derivative, you can write as a boundary term. And of course, at infinity, where you have this boundary, the fields are supposed to be 0. So this does not contribute. Right? Boundary terms you can drop, assuming that the fields goes to 0 at infinity. All right, so that means that this contribution, even though it is not strictly 0, because it is a boundary term, for our purposes, where we assume that the fields go to 0 at infinity, can be neglected, right? So that means that we just have to focus on this term, for which there isn't much to do, and the second one, right? And so as far as the second term is concerned, we need to work out what variation of the square root of the determinant is. And so that can be done again. It's a fairly straightforward thing to calculate. And I'll just give the result, which is that the variation of root g, the variation of root g can also be written in terms of dg mu nu. That is, can be written as 1/2 times the square root of g times g mu nu times dg mu nu. Right? And so that's very simple. The only thing that is left is that what we have here is a g mu nu with the indices up and a g mu nu with the indices down in this case. And that is going to be fixed by the fact that the variation for g mu nu with the indices up is equal to minus g mu sigma lambda g nu g mu sigma g nu lambda times the variation of g sigma lambda with indices downstairs. And this just follows from the fact that g times g to the minus 1 is equal to the identity of the Kronecker delta. So if you vary one or you vary the other, the total variation has to be 0, which means that the variation with respect to the indices up is minus the variation with the indices down. Now that minus sign is crucial. That minus sign is crucial because it does reverse the sign of this term. Otherwise, we would get the wrong equations because we need the minus sign in the field equation. Okay. So we put everything together, right? We put everything together and we find that the variation of the Einstein action, right, is equal to, well, first of all, we have the minus 1 over 16 pi g in front. Then we have the integrand d4x. And then we have the root g, which you can factor out, right? It appears in all of these expressions. And then we have the minus r mu nu, which is coming from this variation, which is the variation we need here. So we get the minus r mu nu. And then plus the r times the 1/2 because of the variation of root g, right? So plus 1/2 of g mu nu. Let me write this upstairs. 1/2 r mu plus 1/2 g mu nu times r, and then times dg mu nu. Dg mu nu like this. Right? And now we use the usual argument that we have when we do the variation with respect to a field or a coordinate, and that is that this variation is arbitrary. So there is an arbitrary dg mu nu of x at every point. And so in order for this variation to be identically 0, we have to have that the integrand is 0. Right? So that implies that we have r mu nu minus 1/2 g mu nu r is equal to 0 in this case, which is the field equations in the absence of matter, right? Now, this is remarkable, right? It is remarkable because we get the field equations which do have two terms, right? We get that from the variation of something that is very simple, right? In fact, it is not unusual already in classical mechanics that the action is simple, but the equations of motion can be slightly more complicated. For example, it applies to the case of particle in electric and magnetic fields that the Lagrangian is simple, and then the equations you get out of that Lagrangian, which is the Lorentz force equation, is slightly more complicated. So here we have something similar. We have that the action is extremely simple. The reason why it is extremely simple is, of course, that there's only one scalar you can construct out of the curvature. Right? So curvature is described by this Riemann tensor, but in order to get a scalar, there's only one possibility, and that's the scalar curvature. Right? So what about the matter part? So the matter part means that you have to add something that contains the T mu nu, right? And so the variation of the matter part, I sub m, is going to be the part that contains the T mu nu. So it's going to be 1/2 times the integral in d4x times the square root of g times T mu nu of x times dg mu nu of x again. And so that is similar, of course, to the interaction terms we have in electrodynamics, because remember, in electrodynamics, you have things like J dot A, or if you have in a 4-dimensional notation, you have J mu, A mu, right? And so this is quite similar, because the analog of the J is, of course, the T mu nu, and the analog of the field is the G mu nu. So the variation of this is what defines the energy momentum tensor. And this part here, of course, is easy to vary with respect to G mu nu, because I already gave you the variation. So you just add this term to the action for the gravitational field. And out here, you're going to get an extra term, which is the T mu nu. Right? So you're going to get minus 8 pi g times T mu nu. Right? And you see that the 1/16 pi g is here from the very beginning, so you just multiply everything out and it goes over on the other side. So this is what happens when you have the matter fields. And so this was an important discovery, right? In particular, if you did not know anything about the Bianchi identity, right, which was what, remember, constrained the Einstein equations to contain two terms, right? The reason why we needed two terms is because it wouldn't work with the R mu by itself. You needed to have the second term so that the covariant divergence of this thing was equal to 0, right? In this case, you don't need to know about the Bianchi identity, because the action, which can only contain R, when that is varied, it automatically gives you the two terms, and in fact, it automatically satisfies the Bianchi identity. So you get what is the right result, and no further thoughts, if you wish, are required at this point, right? So, all right, so this is how you add matter. And now let's go back to the case where you don't have matter for a second. So let's just stare at this a little bit more. Right? And so we have the action for the gravitational field, which is in this form. And, well, again, we might have missed one term. We might have missed one term because, of course, I said that R is the only thing you can calculate or write down out of the Riemann tensor, out of curvature. But, of course, there is another possibility, right? And the other possibility is that you add a term which is the integral d4x of root g, right? If you add this term does not contain the curvature at all. Nevertheless, it is allowed by general covariance, right? It is allowed by general covariance because this is the invariant volume element. So we know that this object here is coordinate invariant. So it's perfectly legitimate to add this to the action, and we can add a constant in front of it. And so we have, again, the cosmological constant. Right? We have, again, the cosmological constant. Right? So the cosmological constant does not disappear. The cosmological constant does not disappear. So lambda is equal to lambda naught times 16 pi g. Right? The lambda we introduced in the other lecture is related to this one by a multiplication by lambda naught. But otherwise, it's the same thing. Right? So whichever way you look at the problem, the cosmological constant is something that is allowed, whether you look at the field equations or whether you look at the action. Right? And so what is the interpretation of the cosmological constant in this context? Well, it just multiplies the total volume of space-time, right? Total volume of space-time, right? And that is certainly an invariant, right? And so it's a legitimate term. Right. Now, the other thing that we should mention at this stage is that the action is used in quantum mechanics as well, because the action is a gateway to the quantum theory of gravity. The action is a gateway to the quantum theory of gravity because we do know, right? How does that come in? Well, that comes in because in the path integral formulation, you use the action, right? So you look at the Feynman path integral. Right? Normally, the way you do quantum mechanics is that you have operators that do not commute. So you have xi and pj. In non-relativistic quantum mechanics, this is equal to IH bar delta ij. Right? So normally, quantum mechanics is introduced by having non-commuting quantities, and that is, of course, the description that also comes out of the Schrödinger equation, because in the Schrödinger equation you can rewrite it in terms of non-commuting quantities. But Feynman had this idea that you can also derive quantum mechanics based on different principles which have to do with his path integrals. So the idea in the Feynman formulation, as you remember, is that the amplitude to go from one point to another, right, according to Feynman, the amplitude to go from point A to point B, or point 1 to point 2, right, if we have point 1 and point 2 in quantum mechanics, this amplitude is obtained by doing a sum over all paths, right, that connect point 1 and point 2, which means you enumerate all possible paths that connect the 2 points, right, something like that. One of which, of course, is going to be the classical path, but only one of them, right? And then you weigh all these paths by e to the I over h bar times the action that is associated with going from point 1 to point 2. So in Feynman's picture, actually, there's no non-commuting operators, right? The operators kind of disappear from the picture, and you get a description which is perhaps more connected to classical mechanics than the operator one, because you have this action, you have the notion of paths, even though they're nowhere differentiable, and then you sum over all these paths and you get the quantum mechanical amplitude, right? And that, in fact, allows you to calculate most quantities that we calculate in non-relativistic quantum mechanics. For example, using the Schrödinger equation, you can recalculate that using the path integral. Sometimes non-trivial, it's a lot of work, but it works out pretty well in the end, and it's an equivalent description. And so why bring this up here? Well, first of all, because we have the action, right? So we know how to formulate something like that. And the second reason is that modern quantum field theory is formulated almost entirely in terms of path integral. So anytime you take a class on quantum field theory where you learn about electrodynamics, but more importantly about non-abelian gauge theories, and you learn about the standard model of electroweak interactions and quantum chromodynamics, which describes the interactions of quarks and gluons, it's all done with the path integral. So the path integral is the way to go. It is, in the case of gravity, also manifestly covariant. So in the case of gravity, right, we proceed the same way. And let me actually erase this. And if we want to understand what the quantum theory of gravity looks like, then the key object is, again, the Feynman path integral for gravity, right? Which means that, again, Z is the sum over all geometries of e to the I over h bar times the action, right? Because the paths for non-relativistic particles are the x's, right? The coordinates that describe the motion of the particle. But if you're dealing with a field, then of course that's the degree of freedom you want to look at. It's the g mu nu, right? Or in this case, you want to look at z, which is an integral over all metrics, right? So it is a functional integral. Right? And that functional integral will involve now the action. And so it's e to the I over h bar times what we call I, right? The action I, which is a functional of the metric g mu nu. And well, what is of course remarkable is that we think we know everything that appears in that path integral because we do know that the action, well, it's given by the Einstein-Hilbert expression, right? We know that that is correct classically, but more importantly, we know that you can't write down any other terms as far as the action is concerned, at least when you include just first and second derivatives of the metric. And this is, of course, what applies also to quantum electrodynamics. There's only one form for the action, which means that quantum electrodynamics is already completely fixed by the classical theory, which is the Maxwell theory, right? So this Ig of here, this I, right, is equal to 1 over 16 pi g times the integral of root gr, right, plus lambda naught times the integral of root g plus the matter part, right? And so if you have the matter part, of course, you'd have to integrate over the matter fields. And the measure is actually something that you can write down explicitly because it's going to be a product of all space-time points of a product over mu greater than nu of dg mu nu of x. And this is called the DeWitt measure. The DeWitt functional measure, because Bryce DeWitt was the first one to write this down in the late 60s, what the Feynman path integral for gravity would look like. He wrote a number of papers. So in this theory, there are no adjustable parameters. In principle, it's a theory that because the classical theory is uniquely determined by general covariance, so is the quantum theory as well, which is also supposed to be general covariant, right? So it is a theory that contains very few parameters. It contains the bare Newton's constant, and it contains the bare cosmological constant, and then it might have some other parameters which have to do with the matter that enters into the action, which could be, you know, ordinary particles, neutrinos, photons, and things like that. But right? So the action is a gateway to the quantum theory of gravity. It is an essential ingredient, and it is unique. And so that is one of the interesting and fundamental things that comes out of the discussion we're having at this stage. Right? Now, to conclude this subject, let me again make an analogy with electromagnetism, right? Because in electromagnetism, the action I, right, is equal to 1 over 4 g squared times the integral in d4x of f mu nu times f mu nu plus the matter part, right? And so this would be the QED, the electromagnetism or QED part. QED part. And well, there are some differences. Of course, there is still a coupling in both, right? And that is fine. It has different dimensions. But in electrodynamics, actually, there is no term that you can construct out of the F only, right? Now, you do remember that F mu nu is d mu a nu minus d nu a mu, right? That is how it's defined. And you cannot take the F and make two indices equal, which would be like the R, right? The scalar curvature, remember that the scalar curvature is some sort of a trace of the Ricci tensor, right? Or of the Riemann tensor, if you want to start with. And if you do that kind of trace for the electromagnetic field, you get 0 because it is antisymmetric in the two indices. And so if you try to set two indices equal, you get 0. So there is no such term. There is no term that you can construct out of the electromagnetic field which has no derivatives either. So there is no cosmological constant term, except, of course, the mass term. You could write down the mass term, but the mass term, remember, is not allowed because the theory is supposed to be gauge invariant, right? So there's basically no analog. No analog, right, of that. And if you wish, there is no analog of this either because the trace of f mu nu is 0, right? So you can say that there is really not a direct analogy. There is an analogy because if you do consider there is an analogy with the f mu nu squared of electromagnetism, right? Because you can have some other terms that look like that. And the possible terms that you can have is that, in fact, you can take the square, right, of r, and you can have r squared. You can also take r mu nu, and you can square that, and you get r mu nu times r mu nu. Right? And these are all coordinate invariants because you construct a scalar, or in this case, you have a two-index tensor, which you contract with itself, which is a scalar. And there is, in fact, another possibility. Well, altogether, actually, it turns out there's quite a few. There's about 6 of them. But so r mu nu lambda sigma and r mu nu lambda sigma is also possible. And there is a few more, right? So you can have something like f mu nu squared. And you can have something like f mu nu squared, right? So I said that you can't have the trace of f, right? But you can take a square of the curvature and get something that is non-vanishing. So why is it that we didn't include these terms? Well, first of all, you can show that actually only 2 of them are independent, because if you take a certain combination of those 3 terms, they give the Euler characteristic, which is a topological invariant in 4 dimensions. So the only thing we can do is have 2 of them. And so that means that you can take the integral in d4x of r squared, and you can take the integral in d4x of, times root g, of course, times root g of r mu nu. And you can multiply this by alpha and multiply that by beta and add it to the action. Right. Well, I just said in the last lecture that the Einstein field equations were kind of unique. And I've argued before that the Einstein action is the only action you can write down for gravity. It gives the correct field equations. And now I'm telling you that you can add these additional terms, which incidentally were considered by Pauli very early on in the 1920s as a possible extension of relativity. So what is the argument against these terms? Why is it that we don't add them on, right? So we would have to add them here, right? So all of a sudden, we started out with 1, which was the Einstein-Hilbert term. Then we recognized that there should be a cosmological constant piece. And now we have these curvature square terms, right? So how are we going to get rid of the curvature square terms? What is the argument why those terms should not be considered? Well, the argument, of course, is that they contain more derivatives of the metric, right? Because you do remember that R, right, or Ricci or Riemann or whatever it is, contains second derivative of the metric, and it also contains things like first derivative squared of the metric or the fluctuation in the metric. It doesn't really matter, right? And So that means that when you square it, you get more derivatives, right? And so that means that those terms are going to be sensitive and important only when you have very wild fluctuations in the metric. Only when the metric is changing significantly from one point to another are they going to be important. So we can safely drop these terms if we're considering spacetimes which are smooth. Right? For smooth enough spacetimes, these terms will be tiny because the scale of variation of the metric is going to be extremely small, and so you can neglect them. But the point is that if you insist on general covariance, you can add all sorts of things, right? So for example, another fashionable topic nowadays is to consider an action, right? An action I, where you have the integral in root gr, right? And then you add something else. And this is something I think that cosmologists and astrophysicists like to work with, and I'm not particularly sympathetic to this point of view, but they say, well, let me take 1 over 16 pi g, and with the Weinberg conventions, there's always a minus sign. A lot of other people don't have that minus sign because, by the way, Weinberg defines the Riemann tensor in a way that sometimes is opposite to the way it's defined in other books. There's difference in sign. So we always have the minus one when we look at the Weinberg convention. So some people, what they do is they say, well, you know, maybe I can fit the data to something that is f times 1 over r. So that's called the 1 over r theory. And you can even have something that is more bizarre, which is 1 over 16 pi g times the integral root g times some function of r. And so this is what some people like to work with. And well, it's completely ad hoc, right? It's completely ad hoc because you say, well, I'm going to add to the action something that depends on r. Why do we think that this is ad hoc the way it is? Certainly, this is the Einstein term, so we always want that. But why is it kind of, I mean, the hope was that when you included such terms, you could then take the cosmological constant to be 0, and that you could fit cosmological data with just the 1 over r, right? So you say, aha, I've been able to fit this astronomical data about distant supernovae to a model that does not have the cosmological constant, and so maybe that's a triumph. Is it? What is the issue with such a term?
Can you get a flat universe?
Huh?
Can you get a flat universe with this action?
Can you get a flat universe? Well, yeah, that might be one of the questions. But irrespective of whether you can get a flat universe, you know, our universe, of course, is not that flat in the end, right? So it's always a question of magnitudes. But why would be, you know, within the context of all the things that we have discussed in this class, you know, never mind observational aspects and so forth, why would it be that such a term, you know, might not be that attractive from a theoretical point of view? Why have a 1 over r?
And we can expand this as a Taylor series and you get all sorts of terms.
Right. So you would think that if you want to write an action that is generally covariant, you could expand, you know, a random function in a Taylor series. And the first thing you would have would be the r term, because that's the one that has the least derivatives. Then you have the r squared term. Well, by the time you get the r squared term, you already recognize that, in fact, restricting yourself to r is already limiting, right? Because, in fact, we do know that there is not just a scalar curvature square, but you can take the Ricci tensor square or the Riemann tensor squared. And if you go to even higher orders, there's more complicated contractions you can do. For example, you can also have covariant derivatives of these things appearing, right? So you can semicolon one of the quantities and semicolon the other quantity and then contract them. So when you do a series, Taylor series expansion of some arbitrary function of curvature invariance, you get everything coming in every possible invariant you can think of. And so saying that the additional term that you write should be 1 over r, as opposed to 1 over r mu nu, for example, is entirely arbitrary, right? And in fact, there is no reason why it should be 1 over r and not 1 over r squared or 1 to the r to the power 1 over 137 for that matter, right? You can have just about any power you want. So there is a reason why we say that the Einstein action is unique, because we are restricting ourselves to the lowest number of derivatives, right? And in fact, if there are no derivatives at all, then we just have the volume term, which is the lambda term, right? So these kind of things are, somewhat ad hoc, right? And you might be able to fit some of the cosmological data with it. And of course, it's very easy to work out what the field equations are if you assume that the action is simple enough. I mean, that's an old trick, right? You assume that it is very simple, and then you can work out a number of things. And so it is perhaps, from that perspective, a little bit of a toy model. So anyhow, if you do an internet search, go on Google and type f of r, then you will get lots of papers which deal with theories that are like that people play around with. So again, before we start discussing some of the applications of Einstein's theory, right, I think from the discussion we have gathered today is that if we look at something like this, we can really put a big box around it. And we can say, right, within the framework of what we discussed today, that this is unique. Right, it's unique. I mean, we do know that you can add other terms, but we also understand that those additional terms are only going to be important when you look at very wild fluctuations of the metric at very short distances. But if you look at long distance phenomena, right, where the fields are not varying rapidly in space or time, then this is unique, right? And so the only price we have to pay is that we have to put up with this lambda term, right? The lambda term, there's just no way you can exclude it, okay? So you can give an argument, though, for the curvature square terms. And so we are going to erase this part and erase all this other stuff, right? And but there is another possibility. There is another possibility. And that other possibility we should discuss. And I think it's a very interesting one. And that possibility, well, arises from a number of considerations. The first consideration, if you wish, that leads to what we're going to discuss, which is the Brans-Dicke or Brans-Dicke-Jordan theory. The first consideration is Mach's principle. That is, these people were bugged for a long time by the fact that Einstein's theory of general relativity somehow does not quite explain the origin of inertia, right? It is based on the equivalence principle, but it does not quite explain why certain objects resist accelerations, right, which is something that we discussed some time ago. The second point was that if you look at the repertoire of particles that we encounter in particle physics, right, or in fundamental physics, we have the photon, which is spin 1. We have, in fact, nowadays, right, the Brans-Dicke theory was formulated in 1961, but nowadays we know that all sorts of other particles have spin 1, which is the W and the Z bosons that mediate weak interactions, and the gluons, of which there are 8 of them, which mediate the strong interactions among quarks. They're all spin 1, right? And then we have, of course, fundamental constituents of matter, which is spin 1/2, electrons, quarks, and things like that, right? But as far as carriers of forces, we have spin 1, and then we have spin 2, right? So graviton is spin 2, is a tensor, traceless symmetric tensor, which has s equal 2, right? And so we have the photon, which is a 4-vector, and that has spin 1, right? And remember, we discussed the reducible representations of the Lorentz group, and we know that the only things you can have which are consistent with special relativity, which is going to be valid, right, and in a sufficiently small region of space-time, which is approximately flat, in that region of space-time where special relativity is valid, you can only have spins which are 0, 1/2, 1, 3/2, 2, and so forth, right? So as far as the bosons are concerned, which are the carriers of forces, because you can't have a fermion to be a carrier of a long-range force because it just doesn't obey the right statistics, right? So that leaves one guy here, which is s equals 0. Of course, it's a scalar, right? Right? And there is no s equals 0 yet. And maybe there is a spin zero field, right? And so we should consider what happens if you have a spin zero field. And well, we're not going to discuss some arbitrary theory of the spin zero field. We're going to discuss this Brans-Dicke theory, which does have some specific ingredients. Nevertheless, it is fairly general. It is fairly general. We will again see that if you couple a spin zero field to gravity, it's highly constrained. You can't write down some random terms. The terms have to obey general covariance again. In particular, if you look at the action, there's only a few terms which are allowed. The other thing is that we are going to assume that this scalar field, right, which we're going to call phi in a moment, well, it should lead to some observable effects, right? It should lead to some sort of interesting physics, which of course implies, what does it imply? It implies that its mass has to be very, very small, otherwise you don't get long-range forces out of it, right? So it's going to be a field that has, right, the graviton has zero mass, the photon has zero mass, and this field is also going to be assumed to have zero mass so that we get something interesting out of it, right? All the vector bosons of the other fundamental interaction, which is electromagnetism, weak interactions, and strong interactions, they're all massless. Well, maybe the W and Z I thought were very heavy. Well, they start out massless because you have this Higgs mechanism. So in fact, they're massless, but you can't tell because the symmetry is broken, right? So, okay, so they're mostly, I think, massless, right? So we're going to have also a scalar which is massless. So let's discuss this Brans-Dicke theory, right? They call this the cosmic field, right? And so this is a Brans-Dicke theory. Right? And well, it's a very interesting theory. There's a lot of things that we can say. In a sense, it is somewhat unique because of the principle of general covariance. It is somewhat of an alternative to general relativity because it does have an extra field, which does change a few things about GR. And it does have some predictions which can be tested already on solar system scales. So in fact, as we discuss later on tests for general relativity, it will be kind of interesting to see how well this Brans-Dicke theory fares, because there's a new parameter which is called omega, which appears in the Brans-Dicke theory, right? So they wrote down this theory in 1961. Wrote down this theory in 1961. I think sometimes the name of Jordan is associated with it as well, which is quite a bit earlier than that, around 1949. So sometimes it refers to as a Brans-Dicke-Jordan theory. And sometimes it is called a Scalar-Tensor theory. Scalar-Tensor theory. And, well, because it does have a scalar, right? Has a massless scalar. And so it is supposed to be an extension of general relativity. And so we have a field phi, right? Phi, which is a function of x, right? And so their idea is that the source for this field, well, what could it be? Well, it's supposed to be some sort of extension for gravity, so it should couple to matter, right? It should couple to matter, so we have phi of x. And the way it should couple to matter is in a general covariant way. And so, first of all, we need some sort of derivative of this field, and then it's equal to some source, right? So some derivative of this field is equal to some source, right? And the source is going to be the matter T mu nu. It's going to be the matter T mu nu. And so that means that actually there's only a few things that we can write down, because you do remember that the covariant derivative of a scalar is equal to the ordinary derivative. For a scalar, you don't have these gamma terms, right? If you have the covariant derivative of a vector, then there is a fine connection piece that you have to put in. And for a second-rank tensor, there's actually two terms you need to add. But in this case, it's just the ordinary derivative, and we just have two of them. And so we have just box of phi. Okay. And box of phi, and well, it's a scalar. By taking the box, you still get a scalar. So what was to appear on the other side is still a scalar. Now, the only scalar you can make out of the energy momentum tensor is something like this. Right? You take the trace. The trace is non-zero in general. Right, so that object is fine, and so now what you do is you bring it in the kind of standard form, which is the Poisson or wave type equation, by multiplying this by 4 pi, which is kind of standard thing, and then you multiply it by a coupling, and that coupling is lambda. And well, I'm following here the standard notation, even though lambda could be confused with the cosmological constant, but it has nothing to do with it. Okay, so this is the Brans-Dicke coupling constant. Right, Brans-Dicke coupling constant, lambda. Later on, in fact, we will trade it for another coupling, which is called omega. It's more convenient to write things in terms of this omega, but we'll come to that in a little bit. All right, so we want to make explicit that this is the T mu nu of matter, so we're going to put an M here. All right, and so that part was easy. That part was easy. What is a little bit more complicated is the coupling of the field to the G mu nu, to the metric, to which we'll come in a moment, right? But first, let's consider the following fact that order of magnitude estimate of phi. Right? And we can do that by just doing a non-relativistic consideration. So let's look at the field phi at a point x. Right? Nothing is time dependent here, so it's just a function of x. And well, according to this equation, right? Of course, in the non-relativistic limit, this just becomes the Laplacian, right? And then we can move over the Laplacian on the other side by taking one of the Laplacian. One of the Laplacian is essentially the Coulomb potential, right? So the field at x, well, its source is matter, right? And in non-relativistic limit, the energy momentum tensor for matter is just the rho. So we can write this as, well, the coupling, of course, is still there. Forget about the 2 pi, because we're just doing an order of magnitude estimate. So this is equal to the integral, right, over some sort of sphere, right, d3y of rho of y. This is the source. Right, and then divided by x minus y. Right, this is the original Brans-Dicke argument, right? And so we can write this as lambda times rho, because we are going to assume that this mass distribution is pretty much uniform, is the same everywhere in the universe, which is okay to a first approximation. So we pull that out of the integral, and now we have just the integrand d3x. Right, and so the integrand d3x, we assume that the things are spherically symmetric, and so we write this as an integral from 0 to some very large r of r squared dr, right, and then divided by r. Right, and this is again order of magnitude estimate, and so we get again up to factors of 1/2 and things like that, lambda times rho times r squared. Okay. So that tells us that the magnitude of the field, right, the magnitude of the field is roughly, right, let's use approximately right here, maybe also approximately, right, is approximately equal to lambda times rho times r squared, right? And so this is of the order of 10 to the 27 grams per centimeter. Right? Why is that? Well, because lambda is supposed to be of order 1. So let me write the lambda here, though, in front again, lambda times. The rho is about 1 proton per centimeter cubed. Right? I mean, the density in the universe is known to within a few orders of magnitude, which are not that particularly important at this stage. We know that the average density in the universe is roughly 1 proton mass per centimeter cubed, you know, give or take a few orders of magnitude. And we also know that, and this we discussed already a few lectures ago, that the size of the visible universe is known more or less because it's related to the Hubble constant, essentially, right? The size in the time is about 13.8 billion years. The size in space is comparable to that, the horizon, and give or take, a few, one order of magnitude, maybe something like this. So R is of the order of 10 to the 28 centimeters. Right? That's the size of a visible universe. And of course, anything that is invisible because it's past the horizon is not going to contribute to this integral. Okay? So what Brans-Dicke and Shama and Jordan noticed is this is the same order of magnitude as G, because G is also 1.33 times 10 to the 28 gram per centimeter squared, gram per centimeter. Right? And it is in fact G to the minus 1. G to the minus 1. Remember, G has units of length squared, right? And we discussed the fact that there is this Feynman argument that G is related to the size and mass of the universe through the horizon size, right? So these are roughly of the same order of magnitude. So same order of magnitude, right? And so that led Brans-Dicke to consider that they are related, that we're talking pretty much the same thing, right? By the way, what is Dicke known for? I actually met the guy. I had the pleasure of having dinner with him when I was a postdoc. And it was a very interesting character because he was just as good at theory as he was at experiments.
Microwave background.
Microwave background. What's the business with microwave? How did Dicke come in with a microwave background? Of course, he knew about it. He was professor of physics at Princeton, right? He knew about this microwave background thing that people had predicted that if there had been a Big Bang, then there would be a background left. And so what happened? Well, he was thinking of doing an experiment to detect it, right? But he got scooped. He got scooped because there were two people at Bell Labs by the name of Penzias and Wilson. And what did they found out? These two characters. That there was a lot of background noise, which they couldn't figure out where it was coming from, right? They were building this microwave antenna, and they were orienting it at Bell Labs. Of course, Bell was interested in telephones, telecommunications. They were looking for certain radio bands where, there wouldn't be noise because that's what you want to avoid.
It was homogeneous also.
Yes. And so they orient this antenna around, and they find that there is this noise that's not going away. So they thought it was systematics, of course, at first, that there was some problem with the antenna, right? And then the problem didn't go away and just was there, and they couldn't quite see. They just recognized that there was about a 3-degree Kelvin temperature associated with this background. And then they talked to Dicke. And Dicke said, you guys, you found a microwave background that people had predicted from the Big Bang. That's what it is, all right? And he was very disappointed. He was very disappointed because he had been thinking for quite a while on how to do this experiment and how to find this microwave background. And these guys had found it. It was exactly where you would have expected it, and it was very clear, and it was a wonderful discovery. So Dicke was very much instrumental in the early developments of that stuff because he's according to what I've heard, he's the person that explained to Penzias and Wilson what they had discovered. He told them that's what it was, right? So very smart guy. And so anyhow, he sets out to build a theory based on what we discussed so far, right? And so the starting point is if you look at these two things, then you would come to the conclusion that 1 over G is phi, right? It's this average field. In fact, you would go one step further, right? And you would say that, in fact, if this has any merit, this theory, then the field, right, is going to be a function of x, right, 4-dimensional coordinate. And that means that also the G is going to be a function of x, right? And now that means that it's a function of x and t, spatial and time coordinates, right? But you don't want to give up general coordinate invariance. So you've learned all these wonderful things from Einstein's reasoning, and you don't want to give any of that up. And so now the effort is going to be put in finding a theory that has the scalar field in it and which is still generally covariant. So you have an additional degree of freedom, which is that phi. That phi is a scalar, and we know exactly what we can and we cannot write down when we have this extra scalar, right? So Dicke did not want to give up general coordinate invariance, but he does want to have an additional degree of freedom, which is the phi, and with this kind of correspondence, right? So the question is, can you make a theory that is simple, not too complicated, right? You don't want to have hundreds of terms, that is sufficiently constrained that maybe you have only one coupling, and the answer is yes, there's basically only one coupling you can write down, which is that lambda. And does it give predictions which are different from ordinary general relativity, and where will you see those predictions, right? So right, so this part that I'm erasing, that is of course still correct, right? So let me write it up here. So we have that box of phi is equal to 4 pi lambda times t mu mu, right? So it couples to the trace, and I'm going to write m here, remind us that it's matter, m mu mu, right? So that part is still there. Phi is a scalar. And the mass for that scalar is 0, right? So effects propagate over long distances. And well, now the other piece comes into it, because that's the field equation for phi, but we also have the field equations for relativity. So r mu nu minus 1/2 g mu nu r is equal to minus 8 pi g times the t mu nu, right? So that's the field equation for general relativity. Well, if this Brans-Dicke idea is correct, then of course the g is going to disappear. The g is going to disappear, and so the g is going to be replaced by a 1 over phi. Okay, so there is no g. G is gone. The g is gone, all right? So the strength of the gravitational field, because of this very simple but nevertheless somewhat compelling argument, is that Newton's constant is related to the Brans-Dicke field, and that Newton's constant kind of disappears and is traded for that field. So then some sort of average of the field will be g, right? So at the end of the day, some sort of average of the field will give us the g, or the g to the minus 1, right? So the g is still in there, right? But it is in the form of a field, which means that the value for Newton's constant that you measure in one region of the galaxy is going to be slightly different from the value of g that you measure in some other region of the galaxy, or maybe in some very far away galaxy, or some other universe, or whatever it is, right? And now, this is not the end of the story, because the field is, well, it's a new field, it's a new particle, right? And so it will carry energy and momentum. And now we see why we put the m here, because there's going to be also a phi contribution like this. So this is the energy momentum tensor of the phi field. Right? And we can write that down too, and of course it is going to have a rather specific form, and we'll come to that in a moment, right? So there are actually two new ingredients, right, to the field equations. The first ingredient is that there is this 1 over phi in front, which is the gravitational constant becoming a field. And the second ingredient is that there's going to be energy momentum for the phi field. It has to be there, right? Why is it that it has to be there, the phi energy momentum tensor? Because the field exists, And if it exists, it's going to carry energy and momentum, right? So we're not allowed to actually not write such a term. It has to be included, right? So it has to be included, which means now that this equation is inconsistent, or is it? Are the new field equations consistent or inconsistent? How are we going to test that? Is there anything that we are going to require that this equation satisfy? Well, it will satisfy some guy's identity. And what is the guy's name? It has to satisfy the Bianchi identity again, right? Because we do know that when we take this part here and take the semicolon of that, which is the covariant divergence, we know that because of the Bianchi identity, this is identically 0, right? And so that means that also the semicolon of the covariant divergence of this part also has to be 0, right? So impose the Bianchi identity, right? Now, it will be more convenient to impose the Bianchi identity if we bring the phi field over on the left-hand side. So we're going to do that first. So we are going to, right, so we're going to take this phi field and we're going to bring it over on this side here, right, and multiply then this by phi. So that means that we have r mu, and we can have some of the indices upstairs or downstairs or whichever way we want to do it. It's equivalent, but I'm going to do it in this way. So r mu nu, one index up and one index down, minus delta mu nu times r, and then close parenthesis, and then, of course, multiplied by phi, right? And then close curly bracket, and now we do the derivative, right? This covariant derivative, which has to be, we know it's 0 for this piece here, right? So it's the covariant divergence with respect to mu, right? And this is equal to the covariant divergence on the other side. So we have the minus 8 pi, right, which we have there. And then we have the covariant divergence. So we first have the matter term, m, right? And so we have mu and then nu and then semicolon mu, right? And then we have the phi contribution, which is the same, has the same kind of indices. So it's going to be a mu and a nu and then a semicolon, mu, and like that. Well, we do know a few things. We certainly do know that the matter contribution is going to be 0 because the energy momentum tensor for matter is supposed to be 0. So we're still going to require that the energy momentum tensor for matter is going to be 0. And the other thing that we do know is that this part here is the derivative of a product. Right? So the derivative of a product means that we take the derivative of each term individually. So this is going to be the expression in parentheses times the derivative of the phi. So the derivative of the phi, we're going to just write that as semicolon times mu, right? And then we are going to get also the semicolon derivative of the quantity that is in parentheses, right, times the phi. So the derivative of a product. But we don't know because of the Bianchi identity this is 0. This is equal to 0. Right? So that we can use. Well, of course, this derivative is not going to be 0 because the field will have some interesting dynamics, and we don't want to assume anything about the field. And so that means that we are left with this piece, right? So this piece has to be equal to that piece with the minus 8 pi in front, right? So we have that r mu nu minus 1/2 delta mu nu times r, right, in parentheses, times the derivative of phi semicolon mu, that is going to be equal to minus 8 pi times the t for the phi field, mu nu semicolon mu. Right? So if you wish, that's what's left over of the field equations, right? So that's the second equation. So we could write that under this one, right? That's the first one. So we have equation 1 and we have equation 2, right? And those two equations are consistent because we did impose the Bianchi identity, and so we do know that everything is good. So what is the problem now that we have to deal with? Well, the problem is to try to come up with a sensible form for the T mu nu for the phi field. So I need to know T phi mu nu, what it looks like. What kind of arguments can we use here? Well, we know it's a tensor, so it will have to be built up of things that are tensors, right? Unfortunately, there's quite a few, because what we can have is that T mu nu of the phi field can contain a number of things which are all legitimate, right? It's all legitimate. Well, we do know that this thing is a two-index tensor, so it has to be made up of genuine tensors or four vectors that are multiplied together. So by the rules of constructing tensors, the first thing that we can have is the derivative of phi semicolon mu and semicolon nu. Right? So you take a derivative of phi, you take a second derivative of phi, you do the derivatives the right way, and with one index up and one index down, and this is a legitimate combination. And well, so that's something that you should have in the T mu nu, except we're not quite sure what the coefficient of this should be. So it could be a coefficient which we call C1. In fact, it could be even a function of phi, and the reason why it can be a function of phi, a of phi, is because phi is a scalar, right? So phi squared is a scalar 2, phi cubed is a scalar 2, so any function of phi you can write down is good. And we cannot use the derivative argument that we used for r mu nu squared, right? It doesn't contain derivatives, so we don't know how to actually order these different terms, so we're just going to write it as a of phi, and that's how Brans-Dicke did it. But so that's not the end of it, because we can have also some other function b of phi that multiplies something else. That is, here the indices mu and nu come from different derivatives acting on the phi, but we can also have the same derivative acting on the phi and have here instead the metric, or if you want, because one index up is one index down, you can have the d mu nu. And so now what you have here is phi semicolon rho and phi semicolon rho again. So in other words, you take the same derivative on the phi, you sum it over, and that's legitimate too. And this is again some arbitrary function of the phi field. And well, you might think that at this point you can stop, but no, you can't, because you can also have c of phi, right, times second derivatives of the field itself. So just one field, you take one derivative with respect to mu and a second derivative with respect to mu. And that also, because derivatives will give you tensors, is a legitimate second rank tensor of mixed character, where one index is upstairs, another one is downstairs. And so the last thing you can have is d of phi, where in fact you take these two indices to be the same, so you take the second derivative of the field, but then you have to multiply that by delta mu nu. So it has to be again delta mu nu, and now these two indices are traced over, and so you get say the box of phi, right? And plus of course higher derivative terms, which we are not going to include, right? So third derivatives, fourth derivatives, we drop it, and so we're down to this. And so this is the most general form you can write down, which is general covariant and contains only second derivatives. Now we take this object here, and we plug it in here, right? we plug it in here, and this is actually sufficient to provide a constraint. So the field equations, the new field equations, give that for those 4 arbitrary functions, we have A is equal to omega divided by 8 pi phi. There's a little bit of algebra involved in doing this, plugging these expressions in. And B is equal to minus omega divided by 16 pi phi. C is equal to 1 over 8 pi. And D is equal to minus 1 over 8 pi. And what is omega? Well, omega is something that is related to gamma. So omega, or lambda, I should say, 1 over lambda minus 3 over 2. So in other words, the original lambda is written as 2 over 3 plus 2 omega. So this is Brans-Dicke parameter. By the way, lambda is dimensionless. Lambda is dimensionless. The original coupling, because phi, of course, has dimensions, right? Because it is related to g. 1 over g is phi. But the lambda itself, the coupling itself, is the coupling itself is dimensionless. So as omega goes to infinity, that is the same as taking lambda to 0. Right? So if omega goes to infinity, the lambda goes to 0. And if the lambda goes to 0, what happens? Well, what happens is, of course, this Brans-Dicke field decouples. Right? It just disappears. It has its own life, which is decoupled from general relativity. So in the lambda goes to 0 or omega goes to infinity, we get back ordinary Einstein general relativity. Right? So you have this new parameter, and as you vary the parameter, you deviate from the original Einstein theory, right? And in the limit in which omega goes to infinity, you fall back into the original theory. And so what was it going to say? So anyhow, we can write down the field equations in terms of the T mu nu, right? And so you recognize that there are 4 terms now and not 1, so the equations are not as simple. Nevertheless, the phi field itself is fairly simple because it's a scalar. So the equations are not too bad. And so this was Dicke's original proposal in 1961, and then the question was, is any of this Brans-Dicke theory consistent with observation? So there are standard tests of general relativity which we're going to look at, right? The precessional perihelion, Mercury, radar echo delay, cosmological tests, millisecond pulsar gravitational wave emission, and things of that sort. And you can now compare what the Brans-Dicke theory gives versus the original Einstein theory and see to what extent this omega is non-zero, right? And well, in the early days, in the 60s, the observational tests of general relativity were not that stringent, but nowadays we have a lot of very accurate experiments. And one finds that, in fact, nowadays omega has to be quite large. Omega has to be quite large, so this lambda term is very small. And so the Brans-Dicke theory, or Scalar-Tensor theories in general, are somewhat disfavored by observational evidence. Well, of course, that just means that this coupling is very weak. But if the coupling is weak, the theory is still legitimate, but we just don't know what that coupling should be to start with. So the theory is not out entirely yet, but it is close to being almost ruled out. Nevertheless, we have to understand that even though it does incorporate some ideas of Mach, right, it does that in the simplest possible way. in which Mach's principle is kind of implemented by a scalar field. And of course, it could be that the actual implementation of the Mach's principle, if it holds, is not in the form of a scalar field, but is something that is more complicated than that, right? But Dicke's theory is nice because it is the simplest implementation, in which you have that G is a scalar, so it does not depend on directions, right? It's just at some point, it's just a number, and there is no indices attached to it. And so it is an interesting theory. I remember what I wanted to add. What I wanted to add is the fact that the Brans-Dicke theory has actually a very rather simple form for the action. And so it can be written in terms of just, and if I can find it, and otherwise we'll discuss it next time, I think. Yeah, we'll discuss it next time. It can be written in an interaction. The action can be written in a way that is just a very simple extension of the Einstein theory, where you have a phi r term. So we'll talk about that next time. And so, any questions or comments for today?
So does this predict a spin zero particle?
This predicts a spin zero particle, yes. It predicts it is based on the existence of a spin zero scalar particle.
Dark matter? Because could it be dark matter?
It could be dark matter, possibly. If it is, of course, a spin zero particle, it means it's relativistic, generally. The candidates for dark matter nowadays are fairly heavy particles with masses that may be out of order tens or even hundreds of GeV. So this would be kind of, relativistic dark matter. And yeah, and to what extent that is a candidate today, I'm not 100% sure. Generally, people don't talk about this as one of the constituents of dark matter because it is massless. You could constrain the scalar already by laboratory experiments, right? Because it will modify interactions, and so it will give deviations from gravity on laboratory and solar system scales, right? So, for example, the precession of perihelion Mercury is going to be affected by this Brans-Dicke scalar, right?
It sounds very similar to the Higgs mechanism. Is it?
Yes. Well, because it's a fundamental scalar. All fundamental. Right. All fundamental scalars will look the same, right? Will look the same because the interaction energy will be constrained by general covariance, and so you will get these collections of terms which have derivatives, and those are the only ones you can write down if you insist on general covariance. Nevertheless, you have to remember that the Higgs field is in fact massive. The Higgs field is massive to start with. It's crucial that in the Higgs mechanism, the Higgs field has a mass term and has a quartic coupling. And the mass term, in fact, has to have the wrong sign so that you get this Mexican hat potential, right? And so in that respect, it is different. This Brans-Dicke field is kind of rigorously massless, right? It has zero mass, and so it could acquire a mass through some kind of radiative corrections. Of course, as soon as it acquires a mass, it doesn't modify gravity anymore, because in order to compete with gravity, you have to be massless. You have to give interactions that extend over very large scales. Otherwise, you have some sort of Yukawa potential that is limited by the range. Remember, the range of the Higgs field is because of the mass of the whatever Higgs is left over, right? Because there's, of course, a Goldstone mode, which is massless, but that's because of the Mexican hat potential. So what is left of the Higgs field has a mass which is 125 GeV. The range associated with that is 10 to the minus 15 centimeters, right? So it is extremely small. It is the fraction.
If it has mass, it should then affect the metric, which could be a long range.
Well, if it has mass, it has really difficulty in modifying gravity on large scales. I mean, the reason why the Brans-Dicke scalar gives long-range modifications, of course, everything modifies the metric, but you want to have modification over very large scales. And of course, when you're talking about modifications to gravity, as I said, in order to compete, you have to have a massless particle. So I think there is some analogy with the Higgs, but there's also differences. There's also fundamental differences. The scalars that we do have in particle physics, usually they're all there to generate the Higgs mechanism. And to generate the Higgs mechanism, you always need a mass, and that has to have the wrong sign, right? I mean, there is a Coleman-Weinberg mechanism by which, in fact, the Higgs potential is generated by radiative corrections, but normally the Mexican hat potential is just put in by hand from the beginning with a mass square term that has the wrong sign. So, yes, but here, I think in this class, right, what we are attempting is to try to understand as much as we can the general principles and what does follow from those general principles. And of course, nature can be a lot more complicated than what we imagine. But nevertheless, if you assume certain things, if you assume general covariance, right, then you can say some things, right, which are quite definite. And that is that you either don't have a scalar, and then you have Einstein's theory. If you do have a scalar, then this is how it couples if it's massless. And so the constraints that come from symmetry are very interesting. They're very powerful constraints that tell you that only certain things you can have. And sometimes it's extremely restrictive. So that is very nice, right? That's very nice. Any other questions? All right, so I'll see you next week.